Well, good day and welcome everyone. So this is another Friday. We've got an exciting webinar on pulsars today. So my name is Christian Sass. I'm the astronomer in charge and wish you a very warm welcome to It's Getting Spring very soon. So I would like to introduce our guest, Evan Lewis, now from West Virginia University. And he is a graduate student there in the fourth year and has been doing some exciting, really exciting work. And I've been talking a bit to you, and I'm so looking forward to this. Evan, how are you?
I'm great. Thank you so much for having me. And I'm also very excited to spread the good word on how exciting pulsars are.
Wonderful. So without further ado, the floor is yours. And just let me know when you want to run the poll and I'll run it for you. Thank you.
Great, thanks. Let me pull up my presentation. I'm going to put it in presenter view and full screen once it loads. Okay, is that looking good on your end? Perfect.
Yes, it is.
Cool.
It is. Go.
Great. Well, thank you. And thank you for that very warm introduction. I'm very excited to be here today and talk about pulsars in general, as well as a little bit about my own research on a very specific type of pulsar called a RRAT. So I'm just going to jump in and get started. I'll talk a bit first about just the overall structure of this talk. So I'll talk a bit about how pulsars are made, where they come from, a little bit about their properties and what makes pulsars so exciting, a bit about the general pulsar science that we do. So how do we search for new sources? Once we found those new pulsars, what do we do with them? And I'll finish up by talking a little bit about my research, looking at the single pulses, the individual pulses from these pulsars, as well as my own research into RRATs. So to get started, pulsars are created at the end of a star's life. So to understand how that happens, we really quickly have to understand the rest of a star's life. So stars are basically giant fusion reactors. They spend most of their lifetime fusing hydrogen into helium in their cores. This is a nuclear reaction that also creates, as a byproduct, some extra heat and light that will travel through the star. And once that heat and light escapes, it will get to us on Earth. That's how we have life here. For many stars, they will just be able to fuse hydrogen into helium, and that's about it. But the heavier and heavier a star gets, the hotter it can get in its core, and the heavier elements it is able to fuse. So if we look at a very, very heavy star near the end of its life, if we kind of took its cross-section, it would look like, and this is a very simplified example, this kind of layered onion of different shells of nuclear fusion reactions. So starting from the surface and going in, we have hydrogen fusing into helium, and then helium fusing into heavier elements like carbon and oxygen, et cetera, all the way down until we get, in the absolute heaviest stars, iron in their very cores. Now, all of these reactions that show up here, when you fuse a lighter element into a heavier element, there is some leftover heat and light energy that is able to escape the star, and that's how stars stay up. That's how they keep themselves propped up against the force of gravity wanting to pull them in, is those fusion reactions. But once we get to iron, we kind of hit a wall, because to fuse iron into anything heavier, you actually have to put more energy in than you get out. So these fusion reactions can't happen, and in the absolute heaviest stars, we'll kind of end up with this core of iron collecting at its center, not really doing much. What happens next is really going to depend heavily on how massive that star was. So if we take a star like our sun, it's kind of on the lower mass end of things. And once they finish burning hydrogen into helium in their cores, they'll kind of puff up and expand a little bit, turning into what's called a red giant. Our star has been burning hydrogen into helium for about 5 billion years, and it's got another 5 billion before it reaches the end of its life. And when that happens, it's just going to run out of fuel. The outer layers of this star are just kind of going to slowly blow away over time, and we're going to be left with a white dwarf. It's just this inert object, no fusions happening, it's just kind of sitting there. For our larger mass stars, we're going to have that core of iron coalescing at its center. And what will happen is once that star runs out of the fusion energy, which keeps it propped up, it will collapse in a supernova explosion. These are extremely energetic events that we can detect even if they occur extremely far away. They're some of the most energetic explosions we can witness in our universe. So again, these will only happen for the very largest mass stars, and what they turn into at the very end will again depend on the initial mass of that star. So even in a supernova explosion, when that core collapses, there are some atomic forces. So neutrons, or the elementary particles, don't really want to be in the same place at the same time. So there are some forces that are kind of keeping them away from each other, keeping them from compressing further. If the star is extremely, extremely heavy, the very heaviest stars, that core of iron will be so heavy that that gravity will overcome those nuclear forces and it will collapse straight into a black hole. What we're interested in is kind of this middle zone here with a neutron star. In this case, the collapse will not take it straight to a black hole, but it'll instead be just a giant bundle of neutrons, and it'll be very heavy. The reason we're interested in this is because pulsars are a type of neutron star. Specifically, they're neutron stars which are rotating very quickly and have very high magnetic fields. So going forward, I may say pulsar, I may say neutron star. All pulsars are a type of neutron stars, so they're the same thing. There are some neutron stars which we can't see as pulsars, but I'll get into the distinction a bit later. So we've known about supernova explosions for a very long time. This picture on the left is an image of the Crab Nebula. It's one of the younger supernova remnants that we can see. And it was created by a supernova explosion that occurred about 1,000 years ago. We're actually able to track the expansion of those, that stellar remnant, and we can see it expanding outward. So astronomers were able to kind of trace it backwards and estimate when this star would have exploded. And digging through some historical archives, they found that this was about the same time and the same position in the sky as some Chinese records indicated that there was what they called a guest star. So a new source of light in the sky that they hadn't seen before with this feeble yellow glimmer. We now know that this was a supernova explosion. And in this case, it just so happened to be an explosion that created a pulsar. So in the very center of the Crab Nebula is a pulsar, which we've named the Crab Pulsar. It's a very highly studied pulsar. We even have some images of it. So you can see here this bright dot in the center. Those are images of the Crab Pulsar, and it's an extremely rapidly rotating pulsar. It spins 30 times per second, which is pretty extreme. So what makes neutron stars so special? This is kind of an artist's interpretation. They don't really look like this in reality, but it gives you a kind of idea of what they may look like. So remember that these stellar collapses that occur in supernova explosions are very radical. These objects start much, much larger than our sun, but this collapse compresses them to extreme amounts of density. So a neutron star is about 20 kilometers across. That's about the size of New York City. But despite being so small, they are still incredibly compact because all that stellar material has not been able to escape the gravitational pull. This is just a giant cluster of very densely packed particles. So to give you a kind of idea of how dense these neutron stars are, I've put up some of the densest naturally occurring materials on Earth. We have solid lead and another heavier element called osmium. You can see here that their densities, if we had a cube an inch by an inch by an inch, they would weigh a little less than a pound. So my first poll question for you, just as a guess, how dense do you think neutron stars are? And I've got a few different options here, so I will let everyone put in what they think the density might be, and then we'll see how everyone does.
Yeah, it's unimaginable. I was just thinking if you bang your head against a neutron star, how that would be.
Well, you would actually have trouble even getting close. There's a really fun effect that also happens in black holes. It's called spaghettification. That is the
Yes.
real scientific term. It's because
Yes.
the force of gravity is so strong, it's so much stronger at your feet than it is at your head that it would just
Yeah.
stretch you apart.
Yes. Okay, we'll give it a few more seconds. We've got about 45, and then we'll share the results.
Oh, I'd like to apologize to all my people who are so
Like metrics, right?
yeah, so used to metric units. I'm sorry. As an American, I'm just so used to imperial units.
But as a scientist, you should be using metrics, right?
I know. But you've got some references here, so you can at least kind of estimate.
Okay, I'll share the results.
Sure. There we are. All right, so most of the audience is one step ahead of me. You're correct. It is way more than 1,000 pounds per inch cubed. As an actual estimate, there are about 20 trillion pounds packed into each cubic inch. As a non-imperial measurement, if you'd like, 1 teaspoon of a pulsar or neutron star would weigh about as much as Mount Everest. So these are extraordinarily dense to the point that you can't even comprehend it. We can't see anything like this on Earth. And we'll see that this drastic change in size and this drastic density is responsible for a lot of the very unique properties of neutron stars. One of the other ones is the conservation of angular momentum. This, if you're having flashbacks to your high school physics class, I apologize. This is essentially the conservation of your ability to spin. So if you imagine a figure skater spinning with their arms out, as they pull their arms in, they will spin faster and faster because they are more compact in size. This is, again, taken to extremes in neutron stars. So our sun takes about a month to make one full rotation. To compare, the average pulsar will make a full rotation somewhere between 1/10 of a second to a second. Millisecond pulsars are kind of a special case, and I'll describe what makes them different a bit later in this presentation, but they can rotate hundreds of times in a single second, which is just, again, mind-blowing. And the final effect that makes neutron stars so special is their extreme magnetic field. Again, this is due to the extreme change in size. So a sunspot, which is some of the strongest magnetic fields coming from our sun, they're about a fraction of a Tesla. That's the unit that we use to measure magnetic fields. And the strongest man-made magnetic field, that's a tongue twister, is about 42 Teslas, and that's in this very complicated and expensive Chinese lab pictured over here. It's not a poll question, but you can kind of guess for a second how strong a pulsar magnetic field would be. And whatever you're guessing, it's probably bigger. The average pulsar magnetic field is somewhere between 1 million to 100 million Teslas. So these are some of the strongest magnetic fields of any object we're able to observe in the universe. As kind of a fun aside, there's a Wikipedia page that has, different orders of magnitude of different magnetic field strengths and what they correspond to. And one of the ones on this page was at 16 Teslas. That's the strength used to levitate a frog. I looked into it a little bit, and there is actually some scientific study where they used a magnetic field to make a frog levitate. So if the astronomy career doesn't work out, there's at least one other lab that I will definitely be interested in checking out. So to kind of sum up everything that we've seen so far, we have pulsars or neutron stars. These are objects which are heavier than our sun. They're between 1.5-ish to 2 solar masses, compressed into the size of New York City, rotating many times per second, with magnetic fields millions of times stronger than anything we've been able to create on Earth. So hopefully I've convinced you that pulsars are incredibly exotic objects and give us the opportunity to study physics that we just cannot recreate on Earth. That's what makes them so exciting. So a question some of you may be asking is, how do we know all this stuff? When we look up at the night sky at night, all the things that we can see, at least with our eyes, are giving off optical emission. This is light in the exact frequencies and wavelengths that our eyes have been evolved to be sensitive to. But there are many other forms of light that we're just not sensitive to. At the high energies, we have X-rays and gamma rays. At the very low wavelengths, we have things like radio waves, and pulsars do not emit visible light. So in order to be able to see them, we're going to have to look for them in another way. Inevitably, whenever I mention radio waves or that I'm a radio astronomer, someone asks me if they're really like radio stations and how do radios work. And I didn't know before I came here, but as a quick kind of analogy for how we detect pulsars, how do radio stations actually work? So we've got radio transmitters. These are things like radio towers, and they are emitting radio waves. So the actual sound that you hear coming from your system, the radio towers do not emit sound, because if they did, we'd be able to hear them wherever we were. What they do is they emit light in the form of radio waves. And you've got an antenna on your car or in your radio or however you listen to the radio. And what it does is it reacts to this incoming radio wave and converts it into an electrical signal. I'm not an audio engineer, but there is some way that the information is encoded in the radio wave and then that gets converted into a sound. The principle is essentially the same for pulsars, but of course, we're not trying to use them to make sounds. So in this case, our radio transmitter is our pulsar. This is, again, an artist's interpretation. They don't give off visible light, but you can see that there are these two beams radiating from the pulsar. These are beams of radio waves. Those radio waves travel through the interstellar medium, and if they're lined up correctly, will end up hitting us on Earth. Now, of course, these radio waves have to travel stellar distances. They're scattered all throughout our galaxy. We've even seen some pulsars in other galaxies. So it's very, we have to really amplify these signals to be able to see them. So our radio receiver, instead of being a little antenna on the top of your car, we have to use these giant radio telescopes. This is the Green Bank Telescope in West Virginia. And essentially, it works like a giant rain dish. So the radio waves will come in, and the dish is designed to specifically reflect all of these radio waves to focus at the end of this arm up here. In this arm is a little subreflector, and eventually in this little box here are the radio receivers, just like your antenna, but of course, a million times more sensitive and designed for different purposes. But from there, it's the same process. It picks up on those radio waves, converts it into a digital signal, and from there, we're able to have our data of these pulsar observations. Now, why are they called pulsars? The reason for that is because they do have these beams of radio waves, but their rotation is not aligned with these poles. So I have a little animation here. What we can see is the rotating pulsar, but the magnetic axis, which is where the radiation comes from, and the rotation axis are not aligned. So we essentially observe them as lighthouses. If we're looking at a pulsar, what we will see is a periodic blip every time that beam of radiation passes by our line of sight. And originally, before we knew what they were, some scientists thought they were some kind of pulsating star. So that's where pulsar comes from, pulsating star. But really, it's just a geometric effect of having this rotating beam of emission. In any talk that I give about pulsars, I always like talking about the very first pulsar discovery because in addition to being a cool story, there's a lot of history of science that I think is important to talk about. So the first pulsar was discovered by an astronomer named Jocelyn Bell Burnell. She was a PhD student at Cambridge University in the late 1960s, and part of her PhD thesis was to build this giant thing behind her, which was an early form of a radio telescope. I know it doesn't look like one, but instead of using these dishes to collect the radio waves, we've just got these long wires, which are similarly sensitive to incoming radio waves. Of course, they weren't building this telescope to try to detect pulsars. No one knew they existed, but they were trying to find other sources called quasars, which are produced at the center of other galaxies with supermassive black holes at their centers. Not important. They were just looking for other cool stuff that emitted radio waves. Now, this was back in the 1960s, and they didn't have all of the fancy technology and infrastructure that we now have. So the actual data was recorded on these chart recorders. If you've ever seen a, in a movie like a seismograph, where you've got this rolling piece of paper and this little pen that sketches out as the paper rolls past it, it was essentially the exact same principle. And while she was studying the output from all of these different observations, she found this repeating signal. It was this very consistent train of pulses. All of them were spaced exactly about 1 1/3 seconds apart. They all had the same spacing. And it really piqued her curiosity because she just felt that this wasn't man-made interference. So she shows them to her advisor, and her advisor says, I mean, come on, there's no way that any astronomical object could be so regular and so perfectly spaced. This is probably some kind of human-made interference. Jocelyn was not convinced, and either way, her job was to continue monitoring these charts anyway. And within a couple months, she had found a second source of these pulses coming from a completely different part of the sky with a slightly different period. So what this confirms is that it's not man-made interference and that it cannot be some kind of extraterrestrial stuff. So for a brief period, this signal was called LGM1 for Little Green Men 1, because there was a not very convincing, but kind of hyped up explanation that maybe this was some kind of beacon from another civilization. But once we discovered the second source, it was pretty much agreed that there's a very, very low probability that there are two completely separate alien civilizations on opposite sides of the sky, sending pulses at what would probably look to them as just some random star in the Milky Way. So this confirmed that these sources were astrophysical in nature. Eventually, once they were studied in detail, it was found that they were neutron stars, rapidly rotating neutron stars emitting radio waves. And this was a huge development because this was actually the first observational proof that neutron stars even existed. This was about 35 years after the neutron, like the particle, was even discovered, and about 25 to 30 years after neutron stars were kind of theorized, but no one had had any direct observational evidence until now. The unfortunate part is this was a huge scientific discovery, and the Nobel Prize was awarded for this work to her advisor and the head of her astronomy group, 2 men, and not to Jocelyn, who did all of the discovery and the follow-up and the analysis. This is kind of universally acknowledged as a snub. In all of her talks since, she is unbelievably gracious about this and says, I'm just so excited that pulsars in astronomy rated enough to be worthy of a Nobel Prize, and I'm just excited that astronomy is, able to discover these things. But since this happened, she has been awarded with basically every other physics and astronomy award under the sun, and in the radio astronomy community is really acknowledged as the woman who discovered pulsars and created this field of pulsar astronomy. So that was in 1967. We had the first pulsar. And if we fast forward to 2023, there are over 3,000 pulsars that have been published. And I want to clarify what that means. So we usually look for pulsars by taking these radio surveys. And the GIF that's showing on the screen right now is a projection of the sky in galactic coordinates. So at 0, 0, here's the center of the galaxy, and this horizontal line is essentially the plane of the galaxy. What we do to look for new pulsars is we'll take a telescope and say, hey, I want to look at this specific region of the sky with this telescope. And you can see these variety of different surveys scanning different parts of, in this case, the galaxy with a bunch of different telescopes. They will discover pulsars, but let's say I discovered a pulsar today. To go from the discovery announcement to actually getting it published, I would have to write up a paper, send it into a journal, they assign me a reviewer, I have to fix their comments, and then I submit it and wait for the journal to accept it. So there are over 3,000 pulsars which have been published in scientific journals, and even more that we have discovered. So thousands and thousands of pulsars. I do want to mention one cool thing about some of these surveys. So you'll see one of them that keeps flashing up on the screen is the A0327 megahertz drift scan. What that means is the Arecibo, it was used the Arecibo Observatory. The radio frequency that they used was 327 megahertz. And what I think is the most ingenious is they took this pulsar survey by just letting the sky drift across the beam of the telescope. So there were many times where the Arecibo telescope had to be kind of locked in place for repairs or for an incoming storm, and they couldn't point the telescope to be able to look at a specific part of the sky, but astronomers realized, hey, the telescope is just kind of sitting there, it could still take data, and we could just kind of allow the sky to drift overhead and eventually collect all this data. And I just think that's a really incredible and pretty ingenious way to look for all these pulsars. Now I want to get to my second poll question. In modern days, we use basically the most sophisticated technology we have to take these pulsar observations, and we want as much information as possible. So if I used one of these radio telescopes and I wanted a 10-minute observation of a pulsar, let's just say with one dish, what do you think roughly the size would be in megabytes or gigabytes, etc.? Are we using interferometry? That's a great question. Let's say for now it's just one single dish. We're just taking one observation with one telescope, not worrying about multiple dishes or anything like that.
That's a very interesting question. Wow.
Yeah, and I'm hoping the spread might be a little wider and people won't immediately catch on. All right, let's see.
Okay,
yeah.
What do you think?
The spread's a bit wider. Again, the vast majority of people have picked E. The answer is actually D, pretty close. And I know that may still, although most people picked a terabyte, even 10 gigabytes for 10 minutes is an enormous amount of data. And the reason for that is we take time samples at extremely, extremely high resolution. So this is just a sample of some raw pulsar data. You can see that it's only 100 milliseconds long, so a fraction of a second. On the vertical axis here are the individual frequency channels. So pulsars are broadband emitters. We can see their signals at over a large range of frequencies. And while there are only, I think, 16 rows here, this actually represents usually hundreds or even thousands of individual frequency channels, each of them taking hundreds of individual data points a second. So just the raw data for a very short observation will balloon to insane sizes. And this, of course, if you're taking an entire pulsar survey, you need hundreds of thousands of these observations to fully cover the entire sky, even if you just get a few minutes at each position on the sky. So you will easily, very quickly amount to hundreds of terabytes. The WVU astronomy computer cluster has a storage space of, I think, 2 or 3 petabytes. So that's like 2,000 terabytes. And we are constantly running out of room. So that should give you an idea of how ridiculous pulsar data is. Because in addition to just getting the raw data, we then need to process it to look for these pulsar signals. So quickly, what do we do? How do we do that? How do we distinguish a real pulsar signal from noise or from some kind of man-made interference? One of the best ways to do this is to look at the dispersion of radio waves. So the pulsar signal has to travel from the pulsar through the interstellar medium to us. So in between us, there is this collection of gas and charged particles and other stuff just kind of floating around. So on the left here, we have a kind of illustration of what a broadband pulse might look like. We've got the high frequency part of a pulse up here and the lower frequency part of a pulse down here. We know just from physics that the higher frequency part of the wave will be delayed less than the lower frequency part of the wave. I was just trying to scroll backwards and it did not like me doing that. There we go. So we have the higher frequency part of the wave getting delayed less than the lower part. So once it arrives to Earth, we will see that even with a single pulse, we will detect the higher frequency part a few milliseconds before the lower frequency part. The degree of this depends on what observing frequency we're looking at, but a great way to kind of distinguish a man-made source of radio waves from an actual astrophysical source is most of the time, if you see a sweep like this, you can say that it is astrophysical. I say most of the time because there's a very infamous example. There is actually, it's still around, the Parkes Observatory in Australia. And for a couple of years, they were detecting these extraordinarily bright pulses that had something very much like this characteristic sweep. But it was really hard to pinpoint where they were coming from. There were very few that seemed to repeat, and there was no physical evidence for what these could be. They couldn't find any correlation. And after years of this kind of being a weird mystery on the back burner, someone figured out that if someone was in the break room of the observatory and they were heating up something in the microwave and got excited and opened the microwave door before it actually shut off, when you open that door and the microwave is still on, the radiation will leave the microwave, and the radio telescopes are so sensitive that it would pick it up. And I guess it just so happened that whatever microwave it was happened to give a signal that might look like this. So you have to do a bit more due diligence, but that's kind of an infamous example. Okay, come on. There we go. So I've talked a bit about how we find new pulsars. Once we found them, what do we do with them? Why do we study them? How can we learn more about them? The answer to all these questions is something called pulsar timing. What this essentially boils down to is tracking a pulsar over long periods of time, getting observations spanning months and years, not contiguous, but once every week, once every month, tracking it over time. So here on the left is kind of our toy model of what a pulsar might look like. We've got its magnetic axis, and the radio waves are coming out of that. Meanwhile, it's rotating. Now remember that this pulsar is giving off light. That's energy. So just like a flashlight needs batteries, this pulsar needs a source of power to create these radio waves. In this case, it's the rotation of the pulsar. So pulsars are defined by being powered by their rotation. But because they don't have any fusion of anything going on in their centers, over time, that energy well is going to get used up. So what we would expect to see is over time, this rotation will very gradually get slower and slower and slower. Using pulsar timing, we're actually able to measure this. And this is a kind of graph of the pulsar population. I know it looks very busy, so I'll break it down. On the horizontal axis, this is kind of just plotting every pulsar. Each point, its position on the horizontal axis is its spin period, or how long it takes to make a full rotation. And its position on the vertical axis is the rate of change of its period. How fast is its period changing over time? So a few big things to notice. We have a huge cluster here of what we call typical pulsars, right? They emit radio waves. They've got spin periods, between a fraction of a second and a second. And one thing I'll point out is the value of its period derivative is extremely small. The units are kind of weird because it's tracking the change in period, which is a time, over time. So the units are seconds per second, which seems kind of silly. What that means is that every second, the period will change by 10 to the minus 15. That's a decimal point, and then 14 zeros and a 1. So you can imagine these are extremely stable rotators. Some of the best timed pulsars rival those of atomic clocks. So we're able to track the rotation and the very, very minute changes in its period over time. You'll also notice on this plot that there are some other clusters that don't really match up with normal pulsars. One of them is down here in the bottom left-hand corner. These are millisecond pulsars. You can see that their spin period is much, much shorter. So there must be some kind of physical difference between them. And the reason for this is they're actually formed using different circumstances. So millisecond pulsars are pulsars just like everything else, but they're pulsars that happen to be in a binary orbit with another star, usually a star that has not collapsed yet. So here we've got our main sequence star. Perhaps it's nearing the end of its life. It's a little bigger and a little puffier. And at the center here, we've got that tiny little white speck. That's our pulsar. Now, because the pulsar is so dense, it is able to gravitationally attract some of the outer layers of this companion star towards it. And what happens is that stellar material, didn't mean for it to replay, but that's okay, that stellar material will start to orbit around the pulsar. Because of the very strong magnetic field of the pulsar, it will induce this material to orbit, and it will kind of pull the material towards it gradually, bit by bit, and there will be a bit of accretion. That's when the material from the disk actually lands on the neutron star. Now, if you remember earlier, I was talking about conservation of angular momentum. This is the same principle, but in this case, the material, which is spinning, is landing on the pulsar and transferring its angular momentum onto the pulsar. So as this accretion process happens, what we will see is that the rotation speed of this pulsar gets faster and faster and faster until we've got pulsars rotating many times a second. The fastest pulsar that we've observed rotates over 700 times a second. That's faster than your kitchen blender. And it reaches the limit that it's so fast that it's just about to like break the neutron star apart. So these are extreme objects. Oh, that's 2 slides. And millisecond pulsars are also really cool because all of this physics going on allows us to observe them outside of radio wavelengths. So, millisecond pulsars, of course, we can observe them using their radio emission, but they've also got a stellar companion, which we can look at with optical telescopes. This accretion process also, the gas gets heated, especially when it lands on the pulsar. It heats the pulsar's surface, and this will give off extremely high energy forms of radiation, things like X-rays and gamma rays. So in addition to using radio dishes, we can use things like the Swift X-ray Observatory and the Fermi Gamma Ray Telescope in order to detect these systems in other ways other than just their radio emissions. So if giant radio dishes didn't really pique your interest, maybe telescopes orbiting the Earth will. Going back to our diagram really quickly, the one last thing I want to mention about this plot is that last cluster up in the very top right here. These are magnetars, and they're a little bit different. They're kind of like pulsars' cousins. So they're still neutron stars. They're still made of the same stuff, formed under the same circumstances, but they've got even stronger magnetic fields, some of the strongest in the known universe. And we think that they are actually powered by the decay of their magnetic fields rather than their rotation. You can see they've got slightly slower rotations, but they've also got, faster rates of spin down, and we think that they're powered by their magnetic fields. So lots of exotic types of pulsars. And I've mentioned pulsar timing a bit, so I'm going to get in the weeds and explain exactly how we do that pulsar timing. The takeaway from pulsar timing is we are making a model of how that pulsar rotates, how it moves throughout the sky over time. If it's in a binary system, we're also modeling that. We're essentially trying to measure every possible physical parameter of that pulsar that we can. So we develop some kind of model that's shown here in the blue curve, but then we continue to take regular observations of the pulsar. And we'll see these regular pulses, which are shown here as the red curve. And what we will see, unless we get it absolutely perfect, which we will never do essentially, is there will be some kind of residual. That's an error in time between when we expected the pulse to arrive and when it actually arrived. Again, that's measured in units of time. We call it a residual, but it's just the difference in time between when we expected the pulse to arrive and when it actually arrived. So this is an example of what a finalized published timing solution might look like. Again, a lot of information. We've got a few main things here, like these top 4 rows here are the sky position of this source, as well as the change in its sky position over time. We've got its spin frequency. So instead of the period or how long it takes to make one full rotation, this is the inverse, or just how many rotations it makes per second, as well as the change in its spin frequency over time, other physical properties, and this one happens to be in a binary orbit, so we're also measuring all that. You can see that this is an insanely complicated model, and also that we're able to constrain these parameters with amazing precision. So the spin frequency alone, if we look at it, we can see that it's 29 point blah, 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 blah hertz. And all of these numbers have a little number in parentheses at the end. That is the error on the very last digit here. So we have constrained the rotation rate of this pulsar to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places. And that sounds totally unbelievable, but remember that this is accomplished by obtaining a ridiculous amount of data over a very long period of time. And what we do is not for every individual pulse, but for many of these observations, we will measure a lot of these residuals. And what this plot is showing on the bottom here is those residuals, or those errors, over time. So on the horizontal axis, this is just the entire observational history of this pulsar. And the vertical axis is the residual, or the error in our measurement. 2 things to notice. 1, all of them are roughly centered around 0. That means that we don't have any systematic errors. We don't have any long-term trends in our model. So what that means is all of our errors are kind of centered around 0. We're getting as good as we can get. What does 0 mean anyway? Remember that this is measured in time. So the errors tend to be on the order of a fraction of a millisecond. And that's the difference in time between our predicted pulse arrival time and the actual pulse arrival time. So our ability to measure these pulse arrival times because of this high time resolution of our observations is down to the order of microseconds, which is what allows us to make these extremely high precision measurements of all of these properties. So what can you do with pulsar timing? The answer is a whole lot of really cool stuff, because like I said, you are modeling everything about this pulsar. So for example, the first extrasolar planet, that's the first planet that was ever discovered outside our solar system, was discovered orbiting a pulsar. And we didn't see it with our eyes, but rather we saw a signature in the residuals that matched something orbiting at a very consistent rate. You can use all, the abilities of this model to kind of figure out what it was, and it was confirmed to be a planet orbiting this pulsar. There are some other really cool things too, which will get a bit into general relativity. So for example, when you have a pulsar orbiting another object in a binary orbit, Einstein's theory of general relativity predicts that as those 2 objects orbit each other, they will emit some gravitational radiation. That's some really weak ripples in the fabric of spacetime. And just like pulsars lose energy because they're giving off light, this binary system is giving off radiation, so it's going to lose a bit of energy. And in this case, that means the binary orbit, the time it takes to make one orbit, is going to get shorter over time. These objects are going to kind of spiral towards each other at the center of the orbit. So this is a Nobel Prize winning work, one of the first binary pulsars ever discovered, I think. You can see that they tracked this pulsar over 30 plus years and faithfully recorded its orbital period, or how long it took to make one orbit over time. So the vertical axis shows the change in that orbital period. And all of these black dots are the observed changes, while the black line behind it is not a fit to the data, but is totally independent. It's the observation, the prediction made by general relativity. And the agreement is mind-boggling. I think it's better than 99.5% agreement. So this was, I think, the first indirect detection of gravitational radiation. It's a confirmation of Einstein's theory of general relativity, and again, it won the Nobel Prize. Now, one day, pulsar scientists are hoping to actually get direct evidence of gravitational radiation using pulsar timing. That could be a whole talk in and of itself, but to make a very long story short, what we want to do is collect a whole bunch of pulsars scattered all throughout the sky and time them very, very well. So we're accounting for all the possible effects that could, play with the time of arrival of those pulses towards Earth. If some kind of object was emitting gravitational waves, as those waves passed through our galaxy-sized detector, as it passes through all those lines of sight from the pulsar to Earth, it'll stretch and compress the distance between the pulsar and us. And it's an extremely small degree, but because pulsar timing is so precise, we should hopefully one day be able to measure correlated changes in all of these pulsars' times of arrival, which could correspond to gravitational waves passing straight through us. This is not my subject of expertise, so I can't get into the very specifics, but just to let you know that pulsars can do some pretty amazing things. I'm going to finish up my talk by talking about my research a bit, which is looking at the individual pulses from pulsars, as well as some special pulsars called RRATs. So this is just a kind of diagram. It's not real data, but the gist of it is that you can see that pulsar data, individual pulses from a pulsar tend to not be very bright. Some pulsars emit individual pulsars, which can kind of jump out from the noise, but for the most part, it's not, an individual pulse would not be extremely bright, except for the very brightest pulsars. So how do we get better observations of these? Usually we do something called folding. What that means is once we find the rotational period of a pulsar, we can take our data set and cut it into chunks that are the length of that period and stack them on top of each other, add them all up. What that means is that the little pulses in each individual pulse will all add up to create a general pulse shape. So this is called a pulse profile. Essentially what it is it's showing us the average shape of a pulse, and its signal to noise ratio, or our ability to detect it well, is much higher than it would be for any individual pulse. Single pulses are really unique. This is real data this time, and this is just an example of how single pulses can change over time. This is 22 straight seconds of observation, and zooming in on the single pulses, you can see that all of them look different. We don't have each pulse looking exactly the same. Why? Well, the reason for that has to do with the way that pulsar emission is created, which is still pretty hotly contested. What we're pretty sure about is the pulsar is rotating, it's got this very high magnetic field, and it induces these particle cascades, something something plasma physics, something something, it creates radio emission. That's essentially all we know. So it's still a very active field of research to figure out how these pulses are emitted. But the takeaway is you can see that there's a great deal of variety in the individual single pulses, and by looking at them and how they change over time, we can try to get a better handle on the emission physics behind pulsars and what causes them to make this emission. Specifically, I like looking at RRATs, or rotating radio transients. These are kind of the extreme ends of pulsars. So I mentioned that most normal pulsars will have pretty consistent emission, but that it's very weak. So essentially, we have lots of weak pulses. RRATs are the opposite. We have a very small amount of brighter pulses. And at first, some people thought that this might be a totally separate type of object altogether, but there's a range of, the level of on versus off. So some RRATs, like the one shown in this picture, you may see some emission, like these patchy moments here and here. It might turn on for a bit, then turn off for a bit, then turn on. Some of them are so sporadic that we may see 1 or 2 pulses an hour and then nothing for a while, and then maybe a couple pulses later. But the reason that we're sure that these are pulsars and neutron stars is if we have enough individual pulses, we can find the rotation rate, we can, over a long course of time, use the same methods of pulsar timing to get those same exact parameters. And what we see is their physical properties match those of neutron stars exactly. They're heavy, they're dense, they rotate with speeds around a second, a little less, they have the same magnetic fields. These are neutron stars. So the mystery is, why are these so different? What is so physically different about these that we're observing them in such a drastically different manner with these individual pulses? There are a few different leading theories, and one of the things that I am trying to do in my work is gather as much data on as many rats as we possibly can to get a better picture of the entire rat population as a whole to see if we can kind of pin down what's going on. So what are some of these theories? One of them is that what we are seeing are just the very, very brightest pulses from an intrinsically weak pulsar. So as we saw, the energy of a single pulse can vary from pulse to pulse. So we might have a pulsar which emits a lot of weak pulses and a few very bright ones, but it might be so far away that all we can pick up with our telescopes right now are the very, very brightest pulses. So while it may look like there's no emission, it may be there, but just so weak that it's undetectable right now. Another theory is that these rats are pulsars which are nearing the ends of their lives. So as I mentioned earlier, pulsars are powered by their rotations, but over long periods of time, that rotation is going to get slower and slower. Depending on the plasma physics, which determines how that emission is made, it's possible that these pulsars are just rotating so slowly that they're running out of the juice to create this radio emission. And these might be pulsars nearing what we actually call the pulsar graveyard, which are pulsars that are just not rotating fast enough to create radio emission. The final theory, which is a bit more out there, but I always like thinking about anyway, is that there might be an asteroid belt or another, set of dense objects orbiting the pulsar. And perhaps, it might just so happen that every now and again, that object will pass between us and the pulsar, and it might block out the emission. This is a bit more unlikely, but I think it's cool and kind of indicates that despite all that we know about pulsars, there's still a lot that we don't know. I'm going to talk real quickly about some of the other work that I do, because as a pulsar scientist, you kind of have to do a little bit of everything. I like to center my work mostly on single pulses and rats, but every now and again, something else will pull you in as well. So for example, I am working on a project that actually looks at a few millisecond pulsars. I'm trying to understand those. This plot on the right here is one of the studies I'm doing of pulsars, which are kind of like rats and kind of not. It's really kind of a gray area. So these are pulsars which sometimes they're really bright and we can use that method of folding to look at them like normal pulsars, but sometimes we can't, and we can only detect a few individual single pulses. So this project that I'm working on is obtaining timing solutions for these pulsars using different methods and seeing, does one work better than another for specific types of pulsars, and where does that boundary kind of lie? And finally, one of the projects that I'm really excited about is I am working on observations of a magnetar. It was discovered in X-rays. Most magnetars, you can't really detect a lot of radio emission, but you can detect high energy light like X-rays. I believe as of 2020 at least, there were only 6 magnetars which you could also detect periodic radio pulses. And we've gotten a data set of radio observations of this magnetar over a very wide range of radio frequencies. And this is really exciting because it gives us the opportunity to study the single pulses of this magnetar and see how it relates to other ones, but also look at how that changes with radio frequency and ask, okay, we already know how regular pulsars change with radio frequency. Do magnetars do the same or not? And that can kind of teach us more about the differences between these objects. The very last thing I'm going to bring up before I finish off is always my favorite fun fact about pulsars. So this is a pretty famous album cover. It's the album Unknown Pleasures by Joy Division, and it's got this really iconic album cover. What a lot of people don't know is that where this comes from are observations of pulsars. So this is from someone's 1970 PhD thesis looking at 12 different pulsars using the Arecibo telescope. And what this person did was he took 80 successive periods or 80 rotations in a row of not just any pulsar, but it just so happens that it's the first pulsar ever discovered by Jocelyn Bell Burnell. And what he did is just kind of took each of those single pulses and stacked them on top of one another. So this is kind of another example of how going from pulse to pulse to pulse, each of them has a slightly different shape, a slightly different total intensity. They peak in a little, different places. And this just shows the vast amount of information you can get just by looking at each individual pulse from a pulsar. So I always think that's just a really cool fun fact. And with that, that takes me to all of the material that I've prepared. I want to thank you so much for listening and for having such great questions. And I'm really excited now to answer all of your burning questions about pulsars and what makes them so cool.